Hi, it's Mr. Krieger. Now we're going to do Unit 8, Part 2, Lesson 7, Scaling Volumes. If you haven't already, please watch the preview for this lesson. It will kind of give you a visual understanding of what's happening, although the lesson gets a lot more complex than what I did in that preview. That preview is definitely not enough. Okay, so we're going to start with a rectangular prism. What's the volume of a rectangular prism that has a length of 3, a width of 4, and a height of 5? Well, you could easily figure that out. It's simply length times width times height, which in this case is going to be 3 times 4 times 5, which is 60. All right, easy enough. Make a prediction. How would the volume change if you double all the dimensions? Well, if you watch the video, you know that it doesn't double or quadruple, but it goes up 8 times. And here we're going to take a look at how we figure that out. And you might say, oh, all I have to remember is it always goes up by 8 times. But that's if you double all the dimensions. We're going to see what will happen if you triple dimensions, quadruple dimensions, or even if you scale the dimensions so that not all the dimensions go up the same way. So pay close attention to the video. Okay, let's find the new dimensions based on the original by doubling the length, width, and height from that original problem. All right, so the length was 3, so now it's going to be, we're doubling it, it's going to be 6. The width was 4, doubling it makes the width 8. The height was 5, doubling it makes the width 10. Now find a new volume. We're going to do 6 times 8 times 10, which gives us 480. So if we want to see how many times bigger the dimensions are, how many times bigger the volume is, simply do the new volume by the original volume, and you will see that it's 8 times bigger. So that's a way to check, because it's something that you could actually use for future types of problems where you don't know exactly how the scaling is going to work. All right. So what would happen if you triple all the dimensions? So what you should be doing is if you have a model with dimensions, let's say 3, 4, and 5, you could literally triple all those dimensions. 3 becomes 9, 4 becomes 12, 5 becomes 15. So that if we do the new volume of 9 times 12 times 15, you get a volume of 1620. Now here's the scale factor way. What you do is you take whatever the scale factor on a side is, which in this case it was 3. That we scaled up, we tripled all the dimensions. But what we're going to do is take the scale factor for a specific side and cube it. Every side, every dimension, length, width, and height, each one counting for a dimension, length, width, and height, that's 3. That's why we cube that. So that's going to be our scale factor for scaling volumes. Take how many times we're multiplying each side by, in this case we're tripling dimensions, and cube it because there are 3 dimensions that we're changing. That gives us a scale factor of 27, and we're going to multiply that by the original volume, which in that case, our case was 60, and we get the new volume is 1620, which is 27 times bigger. So this is our scale factor, okay? So how would you change the volume if you multiply all the dimensions by a scale factor of n? Every side is being increased by n times, by n, by n, by n. So it's going to be n times n times n, which is n cubed. N cubed is our scale factor. You take our scale factor and you multiply it by the original volume, the one that you're scaling, and that will give you your new volume. Okay, so that will work for no matter how you scale up. If you triple, quadruple the sides, this will work. All right, so let's move on to the next page. Okay, we're going to take a look what happens with a cylinder. Let's see what happens when we scale the dimensions of a cylinder. All right, what is the volume of a cylinder with a radius of 3 and a height of 10? Let's leave in terms of pi. So we're just doing a basic volume. Remember, you get this formula on the reference sheet. You know the radius was 3 and the height is 10. Plugging that information in, pi times 3 squared, height is 10. That's going to be 9 times 10. That's going to give us 90 pi. That's the volume in terms of pi. Okay, what do you think the new volume of the cylinder will be if we double the radius and the height? Basically, we're doubling all the dimensions, right? So, you could do this by actually scaling each dimension, but the same type of procedure will work that we did in the previous problem, making a scale factor for that, but we're going to take a look at that in a minute. All right, so what would happen if we double the dimensions? Well, the radius is going to become 6. The height is going to become 20. The volume we're going to compute the same kind of way, but using a radius of 6 and a height of 20, which gives us a volume of 720 pi. How many times bigger do you think that is? Well, of course, it's going to be 8 times larger. We doubled the size. We already learned that when you double all the dimensions, it increases the volume 8 times. By the way, one thing I would keep in mind, height is a singular dimension. It's one dimension. But radius is like 2 dimensions. Why? It's being squared. You could think about it as being the length and the width. So it's a single number that represents both equivalent to the length and the width. All right, so here's a summary for scaling volumes uniformly, okay? And we'll talk about what uniformly means in a minute. It means all the dimensions are scaled up the same amount, okay? So in order to do this, what you do is you take the scale factor that you're given, basically the one-dimensional scale factor, the scale factor of the sides, and you cube that scale factor. That's going to be your volume scale factor. And then you multiply that by the volume that you know, the original volume, and that will give you the new volume. All right, so let's try a problem. The volume of a rectangular prism is 50 cubic inches. They're giving you the volume. What is the volume of the prism after all the dimensions are multiplied by a scale factor of 4? Well, here's our new scale factor. It's going to be 4 cubed, 64. We're going to be multiplying, the volume is not 64. The new scale factor is 64. We're going to multiply that by the old volume, and that's going to give us the new volume, which is actually 64 times the size of the original volume. All right, let's try another problem. The diameter of a basketball is approximately 9.5 inches, and the diameter of a tennis ball is approximately 2.5 inches. The volume of the basketball is about how many times greater than the volume of a tennis ball? Well, we could do this using our new scale factor technique. How many times bigger is the radius or the diameter of a basketball compared to a tennis ball? It's 9.5 divided by 2.5, which is 3.8. It's 3.8 times bigger. But the scale factor is going to be 3.8 cubed. So taking 3.8 cubed, we get 54.87. That's a point, decimal point. I'll rewrite it. 54.872. It's approximately 55 times as large. Okay? Okay, let's go on to the next problem. Okay. In the diagram below, the cone has been scaled proportionally. If the volume of the larger cone is 125 cubic inches, then what's the volume of the smaller cone? Remember, what we're doing is we're going to scale everything proportionately. Now, because we know the volume of the bigger cone, that's going to be our pre-image. This is what we're missing. If you remember, your scale factor is always image over pre-image. Let's call it pre. So Scale factor is, let's see what it says again. If the larger cone, okay. All right, so here we have heights. Let's take a look what the scale factor is. Scale factor can be created by using the corresponding dimensions given, which in this case is going to be 6/8 or 3/4. But that's not going to be the volume scale factor. That is simply going to be the scale factor for a height, which is one-dimensional. If you want to find the new scale factor for a volume, you're going to take that scale factor and cube it. That new scale factor is 27/64. That's the scale factor to use on this volume to get the new volume. Multiply the new scale factor by the volume of the pre-image, and that will give you the volume 52.734 to the nearest tenth. The volume of this image is to the nearest tenth, 52.7. All right, so that we've taken a look at how to scale uniformly, let's talk about what it means to scale non-uniformly. And we're going to do that by going back to question 1, where we had sides of 3, 4, and 5. This was the very first question we did in the lesson, right? And when we're talking about scaling non-uniformly, what we're talking about is not doubling or tripling all the dimensions, but maybe only one of the dimensions, let's say length or width, or two of the dimensions, let's say length and width, but not the height, right? All right, so what happens to the volume if we just double the length, if we just double this side, but we left those sides alone? So this is going to become 6. So the new volume is going to be 6 times 4 times 5, which is 120. And if you remember, the original volume was 60, so basically the new volume, it just doubled. Okay? Because we're only changing one of the dimensions. This is the only dimension that changed. So by changing only one dimension, we're doubling only one dimension, we're doubling the volume. Okay, what happens if we double the length and the width? So the 3 becomes 6, the 4 becomes 8. 6 times 8 times 5 is 420. And 420 compared to 60 is 4 times larger. I'm sorry, not 420, 240. And this is 4 times as large as the original volume, which you know was 60. Okay? Because we doubled this dimension, we doubled this dimension, we did not double this dimension, so a double times a double is a 4 times, our scale factor is 4 times as large. Okay. So, what happens if you aren't given original dimensions? In other words, what if you weren't told what the dimensions were? Like in our problem here, they told us that the length was 3 and the width was 4 and the height was 5. So how would you figure out what the dimensions are? Okay, so first of all, draw yourself 2 appropriate solids, whether it's a rectangular prism or a cylinder or a cone, whatever. Make up your own dimensions and label your original drawing with these numbers, with the numbers that you make up. And here's a suggestion. Use 2, 10, or 100, or any number that is divisible by the numbers in the question. You'll see some examples when we do some problems. If you get decimals, don't worry. Just keep them as fractions. Now again, we're going to try to keep those numbers so we don't get decimals, but if you do happen to get decimals, better off working with the fractions, or if you have your graphing calculator, just keep the numbers in your graphing calculator. Everything will work out just fine, even if you get decimals. Redraw the diagrams underneath the originals and scale the appropriate dimensions. So I'm going to just show you an example of that so you can follow along. This is a strategy that might work for you, especially if you're not given dimensions. Okay, what will happen to the volume of a cylinder if only the radius doubles? Okay, that's weird because I'm not sure how the radius is going to affect the volume. So what I'll do is, let me make 2 cylinders, identical. I'm going to draw them side by side, and I'm going to make up dimensions, right? This one is not going to change. This one's going to stay the same. And I'm going to make the radius 2. I'm going to make the height 2. And on this one, I'm also going to make an identical one, radius 2, and the height is 2. Now they want us to double the radius only. So I'm going to bring this one down. This one is not going to change. I'm going to keep this exactly the same. Radius is 2, height is 2. So this one stays the same. This one, I'm going to double the radius. Okay, so here the radius is going to be 4. The height is not going to change. So now I have my original and my new cylinder with a larger radius, double, right? So let's actually compute the radius from the original. So remember, for a cylinder, it's pi r squared h, pi times 2 squared times 2. We're getting a volume of 8 pi here. Here, again, I'm going to use the same formula, but now I'm going to use the new dimensions. The radius became 4, the height didn't change. Working this out, it becomes 32 pi. Now, if we do a ratio of the image over the pre-image, the pi's will cancel out, and it will tell me how many times larger the figure became. Now, remember I told you that radius is like 2 of the dimensions? So we're going to double the radius, which is basically doubling 2 dimensions. Let's say length and width. 2 times 2 is 4. The scale factor is actually 4, but even if you didn't realize that, you could use this technique to figure out your new volume. Okay, here are the harder problems, and by the way, this last problem is a Regents problem. I'm going to do this problem actually on this piece of paper, just so I have some more room. But you're welcome to use the lesson as it was, okay? When comparing 2 cylinders, now let me just get my notes here ready so I can do the problem most efficiently, right? When comparing 2 cylinders, the radius of cylinder B is twice as big as the radius of cylinder A. Also, the height of cylinder B is 1/3 cylinder A. And we have to figure out that cylinder B is exactly how many times, larger or smaller, the volume of cylinder A. We got to fill in that blank. So, like I told you before, make yourself a diagram, make yourself 2 identical diagrams, and we're going to make up numbers for this. Numbers like 2, 10, 100, those are good numbers, but you also want to take into account numbers that are given in the problem. Now they're saying the height of cylinder, oh, by the way, let me label these. We'll call this cylinder A and B. It says the height of cylinder B is 1/3 that of cylinder A, right? So we got to make sure that we make a height of cylinder A. We want it to be divisible by the number given in here, like the 3. So we're going to want to make sure that this height is divisible by 3. If it's not, it's going to be fine. It's just you might wind up with decimals. To make it easier, if I make this height, for example, 12, which I know is divisible by 3, it's going to be easier for me to get numbers that are whole numbers. All right, and let me make up a number. So again, 10 is a good number. Radius is 10. This is A. This is B. Okay, and again, I'm going to make an identical model here with nothing changed. Okay, now here's what I'm going to do. I'm going to, this one is not changed. Radius is 10, height is 12. But this one, we're going to, what did it say? The radius of cylinder B is twice the radius of cylinder A. So this is getting larger. The radius now is going to be 20. The height is 1/3 of cylinder A. So we're going from 12 to 1/3 of that. That's going to be 4. Now we want to see how cylinder B, again, remember this is A, let's call it A prime, B prime. This doesn't change at all, right? B is changed, right? Let's figure out the volume of our original cylinder, pi r squared h, which gave us pi times 10 squared times 12, which is 1200 pi. I just did the calculations, 1200 pi. Let's see what happened here. Pi r squared h, well, I've got the pi, radius is 20, height is 4. The volume here is going to be 1600 pi. This is like our image over our pre-image. So if we do image over pre-image and put those numbers in, we're going to get image is 1600 pi over pre-image, which is 1200 pi. The pi's will cancel out. This reduces to 16/12, which reduces further to 4/3. So we could fill in the answer here of 4/3 the volume. Okay, make sense? All right, so let me just see if there's anything else. Oh yeah, let me just show you the scale factor way. Scale factor way, we knew that the radius was doubled, but the radius is like 2 dimensions. So the radius was doubled, but we have to square that because it's like 2 dimensions. The height, which is like a single dimension, was multiplied by 1/3. This becomes 4/3. Therefore, we should know that the scale factor on A should be 4/3 to get the volume of B. Just saying. All right, last problem. And I'll also do that on this sheet of paper. Okay. Okay, Jaden is comparing 2 cones. And this is an actual Regents problem. Okay, Jaden is comparing 2 cones. The radius of the base of cone A is twice as large as the radius of base of cone B. The height of cone B is twice the height of cone A. The volume of cone A is what? So again, like we told you, make yourself 2 cones. In the first cone, this is A and B, make the radius 10. I'll make the height 10. Again, we're going to make an identical B for now, and then we're going to see what happens to the cones. So, for cone A, the radius doubled. The radius of cone A is twice as large, so we're making the radius twice as large. So the radius of this cone is now 20. But the height did not change for cone A. For cone B, the radius stayed 10, but the height doubled. And we want to see how the volume of cone A compares to the volume of cone B. Well, now we're going to compute. Now, if you remember, the volume for a cone is 1/3 pi r squared h, which you can get from the reference sheet. That becomes 1/3 pi times 20 squared times 10, which is 4,188.79 ... This becomes, I'm just going to use that formula here, 1/3 pi times 10 squared times 20, which is 2,094.39 ... We'll keep all those numbers in our calculator. Now, since we want A compared to B, we're going to put A on top in our ratio. So that's going to be like our image over a pre-image, A over B, which is 4,188.79 ... over 2,094.39 ... which gives us 2. What we learned is that the volume of cone A is twice the volume of cone B. All right, so you can work on your homework.